Hi, my name is Uzma and I work with Dr. Magana in the Rocketive Research Group. In this video, I'm just going to demonstrate the project that we worked on in summer, which is based on visual haptic simulations. The idea in this project was stemmed during a discussion with Dr. Magana and Dr. Carlson. Dr. Carlson is a professor in the Department of Physics, and she's also the instructor for the course Physics 272, in which all these configurations are taught as a module in the course. So as you can see, these are the initial designs of how the idea was developed. So the suggestions that we had was to not only show the configurations for point charges, but also test some other configurations like line charges, sheet charge, charged ring, then two oppositely charged plates, a sphere of charge, and a ring charge. So this slide gives a summary of what work has been done, and it contains the screenshots of all the simulations that have been developed. These are more prototype simulations, and there's ongoing development work going on in this, and we intend to add more improvisations. So as you can see, there's a point charge, a line charge, a ring of charge, sphere charge, two oppositely charged parallel plates, and there's also the surface charge which hasn't been shown here. So the basic principle in our research work is scientific discovery learning. The concept is basically to combine simulations with some instructional support to increase the effectiveness of discovery learning. And this simulation would more serve like a conceptual model for the students. And what the students would do is they would modify certain input variables and observe certain changes in certain output variables. So specific to this simulation, the students would change the position of the haptics cursor in and around these configurations and see as to how with the distance the electric field changes at different points. Now force is directly proportional to electric field, so the changes that they're going to see is in feeling the force and seeing the value of force in the visual representations. So let me begin with the point charge. So we still intend to keep the point charge as the starting point for these simulations. So this is the simulation screen, and in all these simulation screens there's something in the upper left corner to show the position of the haptic device. There's like a small visual representation, graphical representation of how the electric field changes for point charges. So electric field for point charges is inversely proportional to the square of r, and in this case r is the distance of the haptics cursor from the center of the point charge. So here's my haptics cursor, and I'm going to move it around the configuration, and as you can see, the force is going to increase as I move away from the configuration. So the force is going to decrease by a value of 1 by r square as I move away, and it's going to increase by a value of r square as I move towards the configuration. So coming to our next configuration, which is line charge. So as you can see in this figure, the electric field for a line charge is inversely proportional to the value of r, and we'll quickly see the simulation for that. So as you can see, this is a positively charged line charge, and I'm just going to run my haptics cursor at different points. So the force is maximum near the line charge, and as I move away from the line charge, the force is going to decrease, but this time it's going to decrease by a value of r. And similarly for the other side, and it's going to decrease by a value of 1 by r. Third configuration is in question is a sphere charge. So for a positively charged sphere, the electric field inside the sphere is always going to be 0, whereas the electric field outside the sphere is going to decrease by a value of 1 by r square. So we're going to have a look at the simulation for the sphere charge. So this is the sphere charge, and you can see the electric field lines pointing outwards since it's a positively charged sphere, and the force here is, it's going to be maximum here, and as I go away from the sphere, the value of the force is going to reduce by 1 by r square. And now we can go inside the sphere and see that the force is going to be 0 inside the sphere. When I move out and inside, it's going to be 0. The next configuration is the electric field inside a ring charge. So here you can see in this equation that I'm pointing at is a very complex equation for the electric field for a ring charge. And you can see that there's the value A, which is actually a representation of R divided by capital R. In this case, the small r is the distance of the haptics cursor from the center of the sphere, from the center of the ring, and the capital R is the radius of the ring. So depending on this value of A, this integral turns out to be positive or negative. So as you can see in this graph, the value of the integral increases inside a sphere, so the integral is positive, which means that the electric field increases as we move towards the circumference. And if we move outside the sphere, outside the ring, the value of A is negative, which makes this, the value of A is actually greater than 1, which makes this integral negative. And as we move away from the ring charge outward, the direction of the electric field is radially outwards, and the electric field intensity decreases as we move away from the circumference. So we can see this in our simulation. So if I go back to ring charge, so as you can see in the simulation, this is a ring charge, and the electric field inside the ring charge is actually pointing radially inwards, and the electric field outside the ring charge is pointing radially outwards. And inside, the electric field increases as we move from the center to the circumference. So as you can see, at the center it's approximately 0, and as I move away to the circumference, the value of the electric field increases. Outside the electric field is a negative integral, so the intensity of the electric field decreases as we move away from the circumference. So here it is approximately 25, and as you can see, it decreases as I move away from the circumference. Similarly, we have the configuration for two oppositely charged parallel plates. So when we have two oppositely charged parallel plates, the electric field, so as you can see, this is a positively charged plate and a negatively charged plate, and you can see that the electric field lines flow from the positive plate to the negative plate. And if I move my haptics cursor between these two plates, you can see that the electric field is constant. So we intend to have a guided inquiry mechanism to conduct an experimental study for these visual haptic simulations. And as stated earlier, this is ongoing development work, so we intend to enhance this, and we have already thought of some things that we need to improvise and add changes. So we firstly need to work on making this a 3D representation, and also enable the learners to actually move these configurations and rotate the objects and see how the electric field lines would change as we rotate these different objects. Next, we also want to change the color of the haptics cursor as the value of the force changes. And right now there's no containment of the electric field, so we plan to embed these configurations in boxes so that the electric field is restrained inside these boxes. That's all from my end. Thank you.